It's very kind. Also, special thanks to the organizers for making sure I could come here in person to give a talk, even though now I'm severely jet-lagged. So let's see how this goes. I feel like I'm in a dream. So this might be way more chaotic than I want it to be, but I guess that's always true, so it doesn't matter. My title, of course, is a homage to a paper by Martin Lüscher from like 13 years ago about the Wilson flow, because a lot of the current efforts into trivializing maps are directly or indirectly based on Lüscher's work from like 10 to 15 years ago. When I talk let's try. When I talk about approximate trivializing maps, of course, I'm referring to machine-learned ones or variationally optimized ones, which is a rather new trend. So I'm one of the, I'm a member of this fortunate or unfortunate generation of students that was interested in machine learning and quantum field theory at the same time. In fact, I wrote one of the first papers on applying machine learning to lattice QCD or lattice field theory in 2018. I wouldn't recommend the paper. There's a bunch of garbage in it from my current perspective, but it's a very nice showcase of how far this field is really moving, not just in lattice, and also how far people have come since then. And the most important development for me was to realize that I had to grow up at some point and ask myself what am I really doing? Does it make sense to even apply machine learning to this problem? And I should stop throwing around buzzwords about AI, because AI is not going to destroy or save us. We still have to do that part ourselves. But my existential crisis has been minimal because I was able to realize that what has been happening in this space over the last few years actually is very much related to ideas that have been around since the very inception of our field. And I'm going to show some examples that go as far back as 1975. Of course, it's just reassuring for someone young and naive like me to touch base with the roots of the field, but also more practically, a lot of these old ideas from when people were still trying to solve the lattice QCD path integral with basically pen and paper methods, we can today very effectively recycle using the full power of today's algorithms and computing platforms. And some of these powerful algorithms are from machine learning research, although we never train on any data in this work. So a good example is what you see here, this plot. This is one of the simplest non-trivial trivializing maps in gauge theories. This is basically for a single plaquette distribution. Right, okay. So this is the Haar measure or the residual of the Haar measure on the two unique eigenvalue angles for SU3. And here on the right, it's the same thing, but multiplied with e to the minus Wilson action with beta equals 6. And this is a completely deterministic map between those two densities. I'm going to get into more detail later. And then I'm also going to talk about our attempts to learn maps that are similar, but in much higher dimensional spaces using machine learning techniques. Before I get into any of that, we need to talk about this logo. So I know this is ending, but why Comic Sans? And these two arrows have heads, and these two have them in the middle. That bothers me more than I'm comfortable admitting. Okay, so now that everyone hates me, I can draw the attention to my collaborators. So this is, of course, a collaborative effort spearheaded by our fearless leader, Fiala. This is an actual quote. I'm going to print T-shirts with this at some point. And we do have collaborations with Google DeepMind, Tash in Bern, Michael at NYU in New York, and Kyle in Wisconsin. Okay, so let's get started with the basics. What do we really want? So we have a some lattice gauge theory partition function, and we do a change of variables that gives us this log Jacobian in the exponent. It's like an effective action. And what I call the trivializing map condition is that this log J should cancel out the action exactly, so this is 0 or a constant. And if you have a map that does this kind of change of variables, then that minimizes the relative entropy, or also Kullback-Leibler divergence between the trivial uniform harm measure and the full target measure. And if you have a map that can do this, this actually fully solves the thermodynamic partition function or free energy integral. And I want to emphasize that this is generically much harder than just sampling from some unnormalized Boltzmann distribution. While it would be great to do this, and this is sort of the holy grail of this whole research, we better be a bit more, a bit less ambitious for now. So what we can demand instead is that this thing on the left should just be a different non-trivial action S prime, but which may allow us to solve some computational problem. So one example that I'm also going to mention later is that you can introduce a defect into your action. So you just zero out some plaquettes in principle, and then this changes the whole topology of the theory, which then unfreezes the topological charge. So if you have a map that can get you from a theory where the topology is completely unfrozen to your desired target theory, then this map solves the topological freezing problem. Differently, you could imagine that you just take a different coupling constant, so I just put here a generic capital lambda, but this also emphasizes the RG interpretation of the whole trivializing map business. Of course, Lüscher already noted this in his 2009 paper, but only in this one paragraph, and I think it's worth to explore this this relation a bit more. And also, while the term renormalization group is very specific, I think it's still fine to apply the ideas, even if what you're thinking about is not really an RG transformation. And I think this is well described, and I invoke Weinberg here. So this is from Why the Renormalization Group is a Good Thing, also from '83. I can really recommend this paper. So RG was, of course, invented for curing divergences in high energy physics and later applied to critical phenomena in condensed matter. But you can apply RG ideas even if you're not dealing with a renormalizable quantum field theory. And I believe this paragraph here was the birth hour of the asymptotic safety program. So let's start with the Wilsonian infinitesimal momentum shell integration picture of RG, and I'm going to develop this in the stochastic quantization framework. So take your usual Langevin equation where you have the derivative with respect to the simulation time given as the negative of the functional derivative of the action, and then you have some noise term, and here I multiplied a dimensionless regulator term R lambda to the front, which is a function of the Laplace operator. Of course, there's the corresponding Fokker-Planck equation for the probability density itself, and solving the stationary version of this equation, so just setting it to 0, we can at least formally write down the solution. And this is your usual Boltzmann weight e to the minus s, but we have an additional delta s lambda term here, which comes from the regularization of the noise. And again, we can, at least in momentum space, write it down formally, and it looks like this. And if we use a sharp Heaviside theta function cutoff, then we can even compute regularized noise fields very explicitly. Just involves a fast Fourier transform and setting some variables to 0. And you can see some examples with different cutoffs here. And as you can see, this is smeared out more and more as the cutoff is lowered. How this relates to lattice field theory was worked out in this paper, which also happens to be the very first lattice paper I read in my life. But also this has been known in the context of functional renormalization group theory for a very long time. And of course, the 0 cutoff, no noise limit of this whole thing is the gradient flow or Wilson flow, which Martin Lüscher used to formulate his trivializing map originally. I think this Wilsonian infinitesimal momentum logic can be very useful, and I think that's best encapsulated in this FRG script by Holger Gies, where he says that the FRG, what it really does is it turns a functional integral problem into a functional differential problem. And as we probably all know, that can often be much easier to solve, especially numerically. And also there has been a very exciting, more recent development in this direction, which comes from some mathematicians actually, who proved that certain functional RG or exact RG equations are equivalent to optimal transport problems. And you can also relate these normalizing flows that I'm going to talk about later to optimal transport maps. So just in case anyone is curious about that. On the other hand, of course, we have the sort of position space dual to the Wilsonian RG, which is the Kadanovian style blocking spins together, decimation rationale. So in this case, you would just like to combine locally a couple of fields into one representative field variable. And so compared to the smoothing I showed on the previous slide, this would be more like pixelating. And actually, the kinds of maps I'm going to talk about are more similar to these kinds of decimation maps than they are to the differential maps that Lucia employed originally. And here I just put both of these things together next to each other, just because it looks nice. Okay, so as I mentioned before, these ideas have been around for a very, very long time. So Martin Lucia wasn't the first one to think about this, even though I believed that for a very long time. And so over the past few months, I've done an extensive archaeological survey into very early Lattice QCD scriptures. And I just want to share some of the highlights. And I apologize for reusing this joke. I'm going to retire it by the end of the year. So it started actually in 1975 with 2 papers by Sasha Migdal, who's now, I believe he's a successful entrepreneur, so there is a life after Lattice as well. He basically showed that, at least in 2 dimensions, you should be able to just combine Wilson loops together into larger and larger objects with effective actions, basically by integrating out links. So in 2 dimensions, you can work this out very easily because it's a completely trivial theory and everything works very nicely. But he already realized that for higher dimensions, you run into problems and try to employ some approximations to find recursion relations that give you access to critical exponents and such. That didn't work out so well, but we can hope to recycle these ideas today and actually make this work. This was also picked up by Kadanoff himself a little bit later. And then what should also be mentioned are works by Naunberg and Toussaint on the same thing, and also Rich Brower, who derived a number of very interesting results, especially in the large N limit. This is also tangentially relevant, but it's more for fun and curiosity, so just want you to look at this glorious 1980 CERN preprint, which is a combination of typewriter and handwritten equations. That's what they did back then. And then also this paper here, which is typeset. And this whole paper is about determining the prefactors of a Bessel function expansion for this effective action or SU3 one-link integral. And today I can do this in a few lines of Python and it takes less than a second, but back then I assume it was a major effort and deserved its own paper. So it's just cool to see how far the field has matured. Skipping a bit forward, of course, the paper by Lucia in 2009, then we had these 2 papers by Fiala and her group at MIT. I wasn't part of the group back then. Then I forgot to mention these 2 papers at the last 2 times that I gave this talk. And they are actually more in the spirit of Martin's original idea because they employ HMC and a map within HMC to decorrelate the charge faster. Then this was roughly where I entered the stage. I had previously only worked on flows for scalar fields and pseudo-fermion fields. So we had one paper on the Schwinger model. Actually, Jakob was first. He scooped us on that one. But both of these papers are with exact determinants, so no pseudo-fermions. We had a follow-up here. And then at last year's Lattice conference, there was a proceedings where we actually did QCD with dynamical fermions and pseudo-fermions. Of course, it was on a 4 to the 4th lattice with like a 1 kilometer lattice spacing, so not real QCD, but all the degrees of freedom were there. So that was just like a first demo. And I also want to mention, especially Nobuyuki Matsumoto. So this proceedings is also from last year. He presented a different approach this year, and we both realized in Trento a few months ago that we actually work on very similar things. They're actually mathematically pretty much equivalent, but we do implement them very differently in practice. But just wanted to point that out. And we both haven't published anything, so we haven't scooped each other yet. And then in December, we had this paper, which is, I would say, most closely related to Lucia's original one. And then a few months ago, we put out an update about our approach, now in 4 dimensions. And hopefully this whole thing will continue. So I'm excited to see what will happen. And also, I apologize if I forgot any of your papers. I try to restrict myself to gauge theories because it would be too much otherwise. All right. After this long excursion into the history of the field, let's actually get our hands dirty and formulate explicitly a trivializing map for 2-dimensional U1 gauge theory. And I'm actually going to start with just a single U1 plaquette, so kind of the simplest thing you could think about. Here are my conventions. So just have an angle phi that goes from 0 to 2 pi, as usual, the typical Wilson action. And then here's the partition function for this one plaquette theory. And so the first thing I want to do is I want to do a change of variables so that I turn one of the link angles to the full plaquette angle. So basically, I just define a new variable chi, which is the sum of all the link angles, but I'm singling out the first one, and then I just want to have the full path integral defined in terms of this chi and all the remaining phi 2, 3, and 4. And then the Jacobian of this transformation is trivial. It's just 1, so there's no non-trivial Jacobian factor with doing a change of variables like this. And because we're integrating from 0 to 2 pi, and this is a periodic integrand, we can also freely shift the integration boundaries to go back to 0 to 2 pi, even though they would be different here. And that's actually an instance of using the defining property of the Haar measure more generally, and I will get back to that when we do non-abelian gauge. And so I can formulate the partition function in terms of these 4 variables, where one of them has changed. And then I only have a dependence of the integrand on this plaquette angle, and all the others are independent now. Okay? And so now I actually want to trivialize this integral. And when I say trivialization, I have to make a distinction. So many people talk about trivialization actually mean that you fully integrate out degrees of freedom. That's not what I mean. When I say trivialization, what I mean is that you actually keep around all the degrees of freedom, but you trivialize them, which means that you make their distribution trivial. So you turn their density into a uniform one or into like a Gaussian one if you have non-compact variables. And there is a generic way to achieve this here. So if I define an integral transformation like this, where the argument is in the upper integration boundary, and the integrand is just the same as for the partition function I'm trying to trivialize, then you can very easily show that the Jacobian of such an integral transformation is exactly the integrand, up to some normalization to ensure that you don't leave the compact interval. And so if I insert the inverse of this Jacobian into the integral, so just basic first semester calculus, then this cancels out the integrand completely, gives me some irrelevant constant, and then I have fully trivialized this path integral. So I only have the uniform measures left. There's nothing non-trivial left. And then I just undo the first step. So this is just doing the first step in reverse, doing a change of variables back from the plaquette angle to the updated link angle, which is then phi 1 prime. And I can also say that I push back the update to one of the links. It doesn't really matter which one, but I'm picking phi 1. So this is a lot of math. In a bit more digestible terms, the first thing I'm doing is I'm doing a change of variables from gauged variant quantities to gauged invariant quantities, or at least later when we do non-abelian, the untraced plaquettes are conjugation covariant quantities. Then the trivialization or untrivialization, you might have guessed, actually corresponds to evaluating the cumulative distribution function of this distribution, or if you do the untrivialization, you have to evaluate the inverse CDF, and then just undoing the first step. And for this very simple single plaquette U1 gauge theory distribution, this actually corresponds to inverse transform sampling of the von Mises distribution. You may have seen it before in heat bath implementations for U1, that they use the von Mises samplers. Of course, evaluating the inverse CDF is not the most efficient way to sample this distribution. If you look at, for example, the legacy implementation of NumPy, you will see that they do it with rejection sampling, which is faster. But it's an exact sampler. You can evaluate the CDF of this distribution to numerical precision by just computing a Bessel function expansion for like 15 terms. It's very efficient, and the resulting ensembles have completely identical properties. So we know how to trivialize or untrivialize a single U1 plaquette now. Great. But it turns out that at least in 2 dimensions, we can use this whole logic to at least almost trivialize the full theory. So what you see here is the cosine of the plaquette angle, and I just sampled a field randomly from the uniform distribution. So this is just a Haar measure, so to speak. And I can apply the logic that I showed you on the last slide, just sequentially scanning over the lattice from left to right. I mean, you can come up with any sort of scheme that you want. You could do a spiral or whatever. I think this is the most efficient. So I basically just untrivialize all the plaquettes in the first column. So what it means is that I transform them from being uniformly distributed to being target, Wilson action distributed using the transformation I just showed. And if I switch back and forth here, but you can see that also the values of the plaquettes in the second column are changed by this. But there is no non-trivial Jacobian associated with that change because I started with a uniform measure and I end up with a uniform measure. So again, invoking just the defining property of the Haar measure, essentially. So I'm allowed to continue doing this, skipping a few steps ahead until about here. So all of these plaquettes, just to emphasize again, the degrees of freedom are still there. You can see that they have different values, but they're all now very close to 1. I think the target beta was like 8 or something, I don't remember. And so if I had open boundary conditions in this dimension, then I could just do this one more time and I would be done. And then I would have a completely trivialized 2-dimensional theory. And if I did a metropolis accept reject, it would give me 100%. But the periodic boundary conditions mess it up for us. And I think there's a theoretical connection there also to Gauss' law and all that stuff, but I haven't worked it out. So if I did it to the last column with periodic boundaries, I would destroy the distribution in the first column again. So I can't continue here. I can make progress by now going from top to bottom. So just applying the same transformation to individual plaquettes until I end up with a single 1 plaquette defect in the corner. And I can't treat that one in the same way as I did all the others because then you would invariably destroy one of the distributions of the plaquettes around it. So this is sort of where we have to stop. There's a way to systematically improve this by computing larger and larger effective loop actions. I'm not going to go into detail about this, but this can be used to make the map even better. But even with this single plaquette defect, we can just metropolize it because this is a transformation with a Jacobian that we know. So we can just apply the metropolis accept reject rule. And you can see this is the orange curve here, that the acceptance rate is still decent up to beta equals 12. This is for a 16 squared lattice, but because I'm metropolizing against a single plaquette defect independent of the full lattice volume, actually this acceptance rate is also independent of the volume. And if I apply this first order improvement that I just mentioned but will not really go into, then the acceptance rate is also bumped up significantly. So if I look at the topological charge of this independent sampler, then you can see that it mixes very rapidly compared to just standard heat bath at the same parameters, where I just had one tunneling event in the whole 10,000 sweeps that I did. So we can solve two-dimensional U1 lattice gauge theory pretty much. But it's also, you know, a trivial theory. There isn't even a Bianchi identity or anything. So I don't know how much that tells us. Let's just go to SU3, which is already much more complicated, but we still stay in two space-time dimensions. So here again, my conventions, just the typical stuff, nothing that's unknown. We can do the same change of variables again from one of the links, for example, U1 to the untraced plaquette. So this P here, that's still in SU3. We only have to be a bit more careful to actually start the loop then at this point here, because now, of course, the group is non-abelian and stuff doesn't commute, and you have to apply the correct parallel transport if you want to go to like different loops at different locations. But that's not really that difficult. We could just try to go with this, and you know that SU3 can be parameterized with 8 real numbers, but an 8-dimensional map is difficult already, so we can actually exploit this Wiles integration formula to reduce the difficulty of the problem. So what he proved was basically that for any compact connected Lie group, you can express an integral over a function that is a class function, so it's invariant under group conjugation. You can express that as just an integral over the maximal torus, which means that you integrate the unique eigenvalues, which are 2 for SU3, or the unique eigenvalue angles equivalently. And so just by applying a bit of simple group theory, we can make our lives much easier and reduce this eight-dimensional parameterization to a two-dimensional one. This is how it looks in practice. So what you see is the density in this two-dimensional unique eigenvalue angle space. On the left is just the residual of the Haar measure if you throw everything else out. And on the right, I multiplied it with, again, e to the minus Wilson action at beta equals 6. We could, in principle, work with this, but defining a diffeomorphism from this to this density is problematic because you have regions here where the density is exactly 0, and that can lead to invertibility problems. But you can realize that all these different cells are related by the permutation group S6, I believe. So we can pick one canonical cell, and we just map all of these points into this cell, and we just have to be careful when we undo the whole thing that we map them back into the correct triangle, so to speak. But that's just a implementation headache. There's nothing conceptually difficult about this. So the goal is basically now to go from this density to this density, or vice versa. And I'm not going to give many details about this. I will provide them in my proceedings for Lattice. I'm just putting this here to pressure myself into actually writing it. But so I came up with an approximate solution to this problem, which has a tractable Jacobian, basically just by using differentiable quadrature integration to define the cumulative distribution function in this two-dimensional space. You could also do it with the Bessel function expansions that you use for the von Mises distribution. So in some sense, the Wilson action is a generalization of the von Mises to different groups. But so what I used is a package called TorchQuad, which is based on PyTorch and which allows you to do quadrature integration on a GPU and also allows you to get the derivative with respect to the integration boundary with automatic differentiation. And that's exactly what we need to define the Jacobian of this integral transform that I showed earlier, where the argument is actually in the integration boundary. So the first step is to actually map this weird triangle to one that just has a right angle. And then you can extend the space of support to this box. then this integral transform applied twice gives you a completely uniform density. And then doing some cutting and pasting, we can apply the same in reverse to go to the target density. And this map is fully invertible, so it actually defines a diffeomorphism on the maximal torus. I'm sorry. And yeah, so we can use this to do the same thing for the two-dimensional theory as for U1. And actually on 16 squared lattice at beta equals 6, that gave me an acceptance rate of 15%, which is not great, but it's finite. So I would claim that we can solve two-dimensional lattice gauge theories also for SU3, which also isn't a huge achievement. But at least you don't need to do any machine learning for this. So this map only requires a completely deterministic implementation. All right. Okay, yeah, so 2 dimensions are great, but the trouble, of course, starts in higher dimensions. I just love this picture. So actually, Migdal also realized this in 1975, that higher dimensions are just inherently more problematic. And I want to show why with a few illustrations from this state-of-the-art 3D rendering program. So you have the same thing again. This is my active link that I actually transform, and in yellow here is the plaquette that I want to trivialize or untrivialize. And now if I do that and I change this blue link here, then I don't only destroy the distribution of this green plaquette over here, but also these two. And in 4 dimensions, I would have 2 more, obviously. So we can't do the same thing as in 2D, where we just scan over the whole lattice, because we would actually destroy more plaquettes than we create. And so you can try to unroll this a little bit. So here's just the 2 plaquette thing that I did originally, but you have these 2 chairs in addition. And then assuming you can do that, in the next step, you also want to have the plaquettes that were orthogonal to that, since we're now in 3D. And you run into all sorts of problems where you have to form all kinds of weird loops. And you can see I tried here to find patterns that allow me to tile the full 3D space. But it's difficult, and this is just 3D. And 4D Minecraft does exist, but I don't think I can use this to get any insight. So it's hard, and basically that is what I'm trying to use to motivate why we want to use machine learning techniques for this thing, because one thing that machine learning, and especially deep learning, has been incredibly, at least empirically successful in, is finding very weird and complicated correlations in very high dimensional spaces. And that's what we at least hope to be able to exploit also for this problem. So I'm just going to very quickly share some of the highlights of the most recent paper we put out about this. So it's now, we only focused on 4 dimensions, but everything is basically generalizable to arbitrary space-time dimension. And the central idea is to just replace these cumulative distribution functions that I introduced earlier with something that's parametrizable and can be optimized. And we chose to use rational quadratic splines. You can see an example here, because they're very easy to turn into something that has all the properties we need to actually get a diffeomorphism on a compact group manifold. So compactness by fixing the endpoints. You can enforce monotonicity by imposing a constraint on the derivatives, and yeah, differentiability, and also bound the derivative so that the inversion is actually numerically stable and doesn't go haywire. And then we can just compute the parameters of this spline locally from the surrounding data features, so other field variables or quantities computed from field variables. And we can compute the spline parameters using expressive parametric function classes, such as deep neural networks, but not necessarily so. And I would actually be excited if anyone finds a better parametrization that doesn't require using these black box neural networks, because we have pretty much reduced now the role of deep learning to this very microscopic component. But actually, I think it would be great if we could completely abandon it, but I haven't found a way to actually make that happen so far. And yeah, the global invertibility of such a transformation you can just achieve by doing some masking. So you just transform, let's say, half of the variables in one layer, conditioned on the other half, and then you just switch around which variables you update. So that what I mean by global invertibility is that the inverse and the Jacobian are tractably computable. So they don't take like n to the 3, which you would have with just a generic map. But if you have a masked map that actually gives you a triangular Jacobian, then the cost is only proportional to the lattice volume. Right, and then this whole thing, is a very, very high dimensional parameterization, but it's actually surprising that we can optimize it just with the loss function, which is the Kullback-Leibler divergence or relative entropy that I mentioned in the very beginning. So using the observation that a perfect trivializing map would minimize the relative entropy, you can realize that you can use it as a cost function with which to optimize the whole map. Okay. So that's the basic idea. Then there's a number of microscopic choices about the architecture you have to make. I'm just going to go through them rather quickly. So for this neural rational quadratic spline flow for the eigenvalues, you have to choose a suitable parametrization of this canonical cell. You can't just use the θ1 and θ2 coordinates because you have ambiguities with where the support actually starts. And we found that a polar coordinate parametrization gives the best results. I think this is close to optimal, but there might be better parametrizations of this cell that I'm unaware of, which might improve this further. And then you have to choose a set of data features surrounding, the plaquette or link you want to update. And for this paper, we just picked these basic loops, the traced loops, I should say. But I'm going to get back to this in the end. We realized that these are only the most basic features you could use. And although this whole thing now took like 3 years to realize, it's actually just the most basic architecture you could apply to try to trivialize SU3 gauge theory in higher dimensions. And yeah, you have to choose a local coupling geometry. So what I talked about earlier was just what we call direction coupling. You update this active plaquette, and then you have a passive plaquette here. But it's actually also possible to do what we call location update, where you have 2 active plaquettes and 2 active links, and they share one passive plaquette. And you can also generalize this to higher dimensions. So this is how it would look in 3D. And all these plaquettes, they have no overlap. None of their links touch, which allows us to do this tractably. Then the masking I mentioned. So of course, you can handcraft masks and test them, but you don't really want to do that because it's a lot of work. So we designed an algorithm that gives us automatically suitable masks, and that also allows us to alternate the masks so that there are no blind spots in the whole flow transformation. We want to transform every degree of freedom at least once. If you're interested in this and want to have interactive visualizations of these plots and try out different masking patterns, I just recommend that you look in our Jupyter notebook that we uploaded together with the paper on the archive here. Okay. And then for training and evaluation, so I'm not really going to explain what the ESS is, but if you don't know it, it's very closely related to the acceptance rate for metropolis sampling. You just don't need to construct a Markov chain for it. And we realized that having a clean gradient signal is very important to train these architectures. And we also tested this idea that if you have a prior that's not the Haar measure but has some finite beta that you get from heat bath where the theory is still unfrozen, then you should also be able, by having a shorter trajectory for your thermodynamic integration, also have better performance, and that actually happens. Of course, these parameters here are very trivial. Nobody has to tell me that. It's 8 to the 4th beta equals 1. But as I said, this is only the most basic thing, and we've made so much progress even since May, since we uploaded this paper, that practical applications are actually within reach. And here I'm just going to blatantly copy slides from my collaborator Dan Hackett from the Lattice conference. I think I'm almost out of time, so I'm just going to rush a bit. The first application, which we will also write about soon, is you can use flows to generate correlated ensembles, which then allows you to do things like Feynman-Hellman, where you want to compute derivatives with respect to the lattice spacing in one dimension, let's say. And that can give you great advantages in signal-to-noise over having independent ensembles at the 2 points where you then take the finite difference. Hope that makes sense. And then for parallel tempering, so if you don't know, topological freezing has actually quietly been solved a few years ago with this parallel tempering approach, but it requires you to run like 30 chains in parallel. That's not really practical for very large lattices, and flow transformations can help you increase the swap rate so that you need fewer chains. And we actually showed that this leads to an increase in the swap rate if we just use a very simple flow, just transforming from beta equals 6 to 6.05. Okay, yeah, perfect. I'm almost done. So in summary, I showed that two-dimensional gauge theories are trivial, can be trivialized almost trivially. And I showed some proof of principle results for machine-learned maps in higher dimensions. Yeah, I think I mentioned all of this. So these gauge invariant quantities we use as features are really just the most basic features, and we're going to write something soon about what else to use, which makes everything infinitely better. I also think that this proliferation of defects in higher dimensions that you get is a geometric problem, and it suggests to me that we should be using hierarchical or multi-scale architectures, and I believe Dimitrios will talk about something similar later. And then, yeah, I tried to convince you in 1 minute elevator pitch that practical applications are already here. And with this, I'm going to close, so thanks a lot.